All right, so good evening, everyone. I'm Christian, and this is George. We both work at Nomadic Labs in Paris. I suppose you have heard of us. This evening we came here to present you a project that was born in Nomadic Labs last year, I would say, and that nowadays is taking off on its own. It's going to be a kind of spin-off, and this is the first time this happens at Nomadic Labs. So I think it's the right moment to tell you what's going on and what likely is going to happen now. So this presentation is called LIGO / Marigold. You will understand why there is a slash very soon. Basically, it's about smart contracts and layer 2. All right. So I didn't know the audience, so I started with a personal introduction. I can make it very quick. Basically, what I did in the past is I used to work in universities around the world as a professor in computer science, and I spent some time. I've been in the private sector, and this mix of academic background with, I would say, an interest in compilers and theoretical computer science was of interest to Nomadic and to me. I have also a great interest in functional programming, and this is why I even have a book published here at King's College London, by the way. It's so Nomadic Labs, I don't know how much you know about it. Perhaps of interest to you is to know that we are now around 35 engineers. I would say that at least 3/4 of us we have a PhD in informatics. We focus on the research and development of the Tezos, the blockchain. I mean the software, the piece of software, but also the technology. So this is the research, and but not only that. So of course, for example, today we are going. I am not going to represent the majority of the work done there because I'm going to speak about LIGO. And there is also worth mentioning that Nomadic Labs is the home of Cortez, which is a wallet for Tezos. It's a mobile wallet. We also do training. Okay, so I started with very general things because I had no idea who you were, and actually I realized that Arthur covered some things. Perhaps, so yes, he was talking about stack-based. One thing perhaps he didn't insist about Michelson was the type system. Michelson was designed with a very precise idea of what a correct Michelson program was, and this was instantiated in the type system. We will talk about the properties of this type system later, because in LIGO we aim at having the same properties. One thing also Arthur didn't mention, perhaps because it was obvious, that one perk of having a stack-based language is that the code is very compact. And I am older than Arthur, so I remember the 90s very well, and we used to enjoy a lot stack-based languages because they were very compact. And you may remember that, yes, the Java bytecode was born at the time. It's CameLIGO bytecode was also stack-based. For that reason, code was very compact. You don't have to explicitly mention the stack. All right, it's implicitly there. To describe what is a type system, I used a very perhaps too simple example of an instruction in Michelson, which duplicates the top of the stack, and this was an introduction to explain what is the static semantics, which is about typing instructions, which is a way to control and check how you compose instructions. And so the dynamic semantics, which is actually basically what evaluation or interpretation means for us. Perhaps it wasn't mentioned. I think it's in my slides earlier, but because of the necessity to account for the cost of execution of Michelson contracts, it was deemed very useful to have an interpreter. I mean, this is obvious because in Ethereum you also have these virtual machines as well, but this is the basic reason, because you could then try to so there is an ad hoc model for the cost of, in terms of gas, for each instruction in the Michelson instruction set. And currently, as Arthur mentioned before, there is even a statistical study being done at all kinds of labs for a while to have a more precise model, better estimation of the cost as well. So this is really important. But this is also why Michelson has to be interpreted, right? Maybe this is obvious, I don't know. Perhaps something that wasn't mentioned before is that the type system of Michelson is rather simple, and this is good also because we want type checking to be efficient. This is not something that we think of when we use mainstream programming languages, but we have to understand and remember that contract type checking consumes gas. So before you run a Michelson program, you always type check it, and you have to pay for it. So it's important that this goes fast and in some sense is cheaper. I mentioned before that one interest in having an interesting type system is to check for composition of instructions, which means also to safely how can we check the safe composition of contracts. Perhaps we shouldn't call them call, but activations, I don't know. The important properties are here. This is the things we want to achieve. If once a contract passes type checking, what can be sure about? It is important. If it passes type checking, it cannot fail due to inconsistent assumptions on the storage or on other values that are passed around in the code. Worth mentioning is that we have no null values, no cast or cast that can fail, but of course, we can still have, like in your more familiar programming languages, the typical other reasons to fail, which are division by zero, token exhaustion, or gas exhaustion. And we also have an explicit failure instruction. All right, of course, these ones are there for a reason. But important thing is that we can't fail because of inconsistent assumptions. So this lack of inconsistency is called type safety. And another very useful property that is satisfied by the Michelson virtual machine, so the semantics, is that we have the progress property. We cannot remain stuck. All right, this is also very important. And this is really bread and butter if you do programming language theories. You want these properties for your language, okay? So we have those properties in Michelson. Arthur mentioned formal methods at some point, and I heard that for some of you these words are big words. Perhaps it's worth explaining a little bit because when we present Tezos to outsiders, or they are, one of the talking points is to mention that we do some formal methods and plan to do even more. So what does it mean? Actually, there is something I forgot to say here, but for instance, we already use a cryptographic library called HackleStar, and this library was actually, the code was extracted from a specification and a formal proof that the cryptographic functions do what they are expected to do. I don't know that work, but we had a presentation, and this is a team from INRIA that did it. So we actually, in the protocol, use that library. And it's formal methods because we have mathematics to prove that the code is correct. Another reason to speak about formal methods is to say that we have a formal specification of what a Michelson program means, which is twofold. It's the type system and how you evaluate instructions. We come to an example later of what this means in practice. So I'm not sure if you are familiar with a proof assistant called Cog, but this is basically a piece of software that can be used in two main ways. One is for mathematicians to mechanize some proofs. Perhaps you heard of famous theorems that have been proven by Koch, and this is of interest to mathematicians mostly. For computer scientists, Koch is of interest because you can, after specifying, let's say, a system in general, you can extract code that is provably satisfying the properties you proved. Okay. And you can then take that code and integrate it in your own, right? Either as a library or link it dynamically or statically, or just integrate it in the build system. We have this for Michelson. We have an interpreter also that has been extracted from Koch. It's not in the current release, but it's planned to be integrated as well. Some smart contracts have been already, some properties of some smart contracts in the finance sector have been already proved, also formally proved in Koch. So we know that they actually do what they claim they do. Well, I think this is perhaps the best way to explain what is formal methods in Tezos, and we plan to do more of those things using Koch to generate some more critical code, to gain more confidence in some critical parts of the blockchain, and to prove more smart contracts. This is also very important because we hope that people will be, enticed to handle higher stakes contracts that way, if they know they are safe in some precise sense. I wanted to give you some code because I heard that many of you were programmers, so perhaps I thought of a very simple Michelson code. So this is taken from a paper that was published last month by some colleagues of ours, and it's just a simple voting contract in Michelson. Basically, you have a vote that is open to all peers. When I say peer at this stage of the presentation, I mean peer not in the sense of peer-to-peer network, but it's the association of basically of an address and an account. All right, so it's you can be a physical person, can be several peers on the network. All right. Just beware. I wanted to call it participant, but there was no proper way to peer is fine, it's very short. Anyway, so you can vote on a fixed list of candidates and of course with a fee. All right? So how would you do this in Michelson so you get an idea? And you have to define the storage. So here we are going to map candidates to the number of votes. And when you activate the contract, remember this is the storage, this is what is modified by the contract, so only the contract can modify it. And the parameter is when you activate the contract, so this is your vote, or ballot if you want, okay? So now we start. So you start, execution of a Michelson starts with so this represents the stack, okay, growing this way. You have a pair made of your vote and the storage, all right? Remember, this is the parameter and storage. This is always how you start your program. So the first thing is to check that you actually are paying the right fee for voting, okay? So this is done by the instruction amount. This is going to push, so this means const push on the stack. So this is the bottom of the stack, this is the second level. You push the current amount that was paid. Then we push the fee that we expect to be paid. So we push 5,000 new Tez. This is a millionth of a Tez. So we don't have fixed point arithmetic, all integers. And then we compare and we check whether we paid enough or not. So if we didn't, we fail. And if we did, we can either continue here or just pass through because this is going to stop the execution at this point. All right, you can read all the details, but I want you to get the gist of it. So now, if we are okay. Sorry, yes.
We want to repeat the first instruction, the previous slide. So what is amount between parentheses for?
So amount, yeah. So all right, okay. Then I will go slower. Amount is one of the instructions in the Michelson instruction set that actually deals with the blockchain, and it's going to check because when you call your contract, it's a special transaction where you have a parameter, of course a sender, and also an amount of token. Okay, it's just like it's a special transaction, and amount is going to push on the stack managed by Michelson. That amount that you receive with the transaction. Okay. In the same way, you can check the balance. You could check different things which are dealing with the blockchain itself. Yes.
The amount of gas, do you mean?
No, this is the fee. The fee you pay when you talk to the contract. It's a transaction. So you call the contract, telling who you are, and you want to transfer a fee to the contract in exchange of a service, basically. You can think it that way, as a service. So you want to vote, you pay for doing so, but you have to pay enough. That's a way to illustrate that. Yes, did I answer the question?
So what does the parameter in parentheses, so I mean it's a comment, but for vote and storage, how do they relate to amount? That's what I'm not sure to...
This is implicit, yes, okay. I didn't show you how you actually call the contract, but if you would call the contract, you would, so you have the node and the client, which is the command line way to talk to the node. When you use the command line to actually call the contract, there is an option that says how many new Tez you are sending actually. Yes, the contract has an address.
The hashes are comments here. The actual Michelson code is...
yes, this is the comment. Yes. So when you activate, you call the contract, you say the address of the contract, which is a way to say which contract you are actually calling, and you actually say who you are. And it's like a transaction, and you say how much money you send, and then there is the parameter, and the parameter is different, but it's also there, that says, depending on the contract, depending on the type of the contract, in this case it's a string, because you vote for whatever it is, you are voting. So fee, so address, a fee, and then it depends, it's the parameter. This depends on the service you expect to get from the contract. Okay? But yes, there is a fee implicitly. It's a transaction. And we'll come back to this, but of course, if you failed, the fee is collected as well, so you have to be very careful. This is a way to avoid spamming attacks as well, by having failing, anyway, we'll come back to this, but this is the idea. Okay, sender, fee, and then the parameter. Now, just to show you a bit of the logic. So, what do we do? And this is interesting because when we talk about LIGO, we won't have to do this. So but I want to show you how you would do it in Michelson currently, right? So, so we want to check the current number of votes for. So, if you vote for someone or something, and the contract wants to check how many votes have been already cast for that candidate. Okay. So DUP is going to duplicate the element. This is one element in the stack. Now it's duplicated. We have to destructure that element on the top. So instead of having one element that is a pair, you have two elements now. All right. It's a bit tedious, but we have to understand how it works. And now we have vote, a storage. We can check the map. So we want to see in the storage. Remember, the storage is a map. All right, from candidates to a number of votes already there. Get is going to check in the map how many votes are there. We have two possibilities: either known, or there is already an amount of votes that have been already cast for that candidate. Okay, so this is OR. So what do we do in each case? So we have to check what happened. If we had some vote already cast, we want to add one more, right? Basically, because so we push int 1, we add, and we create sum of it. So we have this on top of it now. All right. Instead of this, we did +1. Now we want to update the storage. Remember, we have the stack and the storage. Yes, this is what the Michelson program is handling. Okay. We have to update the storage. We have done our calculation in the new calculation of number of votes in the stack, because this is only what we have, right? Now we have to update the storage and say, okay, we change the number of votes for that candidate. All right, so we need to find, we need to fish out, as I said, the vote. the vote is here, right? We want to associate the vote to this new number of votes for that candidate, right? I should have put candidate perhaps here. Anyway, so we have to do deep and unpair. It means go to the second element of the stack, which is this one, and then apply this instruction, which is unpair. We have seen it before. Unpair takes a pair and creates two elements in the stack. So instead of having a pair, we have two elements here. Can you see the change? All right, we are going there slowly. It's purposefully slow, my presentation, because it's something that we won't do again in LIGO. We have to reorder the two first items like so. So we call swap. Swap is going to take the two first elements on the stack and do this. So these two are going to be now like this. Do you see why we do this or not? Haha. Because now we are going to have the vote, the correct number of the new amount of votes, and now we are ready to, and the storage is here. So we update the storage. So we call update. We have the arguments in the right order in the stack. So now the stack contains a new storage, updated storage. And if you remember what Arthur said before, this is how a normal execution of a Michelson program goes. At the end, so when you start, you have a pair, one element in the stack made of the parameter and the storage. And when you finish, you have a storage. Perhaps the storage is updated, perhaps it isn't. It depends on what your contract logic is. Okay? In this case, we want to update the storage because we want to register the vote. So this is what I say here, and sorry, and we are almost there. I wasn't quite finished. All right, operations. It's not over because we need to return a list of operation. So it's a pair made of list of operations and the storage. But here we don't have any operations. Okay, it's a very simple contract. All it does is to update the storage. It doesn't say I would like to call other contracts or transfer an amount of tokens from A to B. No, it's very simple. So no operations, we only have storage. And now we have the right configuration for the stack to terminate. Okay? So if you want to look again, this is what this is this very simple voting contract in Michelson. So you have noticed we had to swap things, duplicate stuff, go below, fetch it, destructure, right? Okay. Because we only have the stack, okay? So yeah, we had to sometimes go deeply. Sorry? Yeah?
How many elements are you able to put on the stack?
I think there is a limit. Do you know in the protocol?
1,000 or 10,000 something like this.
Yes, it's in the several thousand elements. Yeah. Yes?
Yeah, another question regarding the stack. How deep can you have a stack pointer, I guess? And how deep can you go into it?
He's the expert on this because he proposed new instructions to work on deeply in the stack. Yes, you can. Currently, we are limited. Michelson has macros, like many assembly languages actually. So these are instructions that actually are decompiled or compiled into a series of atomic basic instructions. And we have, for example, if you want to go two elements below the top of the stack, instead of deep, you would write deep. So you would repeat I, right? But you have to write it down. So it's uncomfortable because you have, at the time of writing the contract, you have to know, and it's fixed. You don't have a way. So until now, you didn't have a way to say, I want to go deep and levels. And this was a problem.
You would pay the execution costs at each step. So if you wanted to go 100 levels down below to fetch some variable that was in the environment but very deep below, you would pay 100 steps of execution. Thanks to the fact that we have this self-amendment thing in the protocol, as Arthur mentioned, we were able to add some new instructions to Michelson, including one we can just say, I want to go down to this depth. So it's not exactly a stack pointer, but it serves the same purpose.
Yes, so the limitation was there because the cost of going down. The deeper you went in the stack, the higher the cost. So Georges made this proposal in Babylon, the new amendment that is currently being voted. on Tezos to have a special instruction to go deeper and cheaper.
Yep.
Me, thank you. And so you say you can have 10,000 items on the stack, but these items can be very large. They could be big hashes. They
There's
could
also
be,
a limit on that.
They could be these ints as long as whatever. So
Yes.
is there some defined maximum, or can one say this server its maximum is a gigabyte, that server its maximum is half a
Basically, you have a limit on the amount of gas that you can consume during the execution, a single execution of a contract. And so even if you tried like to make a binary tree by just duplicating, you know, like the usual tower of pairs that are both pointing to the same stuff, actually in memory, the size of it would be very limited, constrained by the amount of gas that you can spend. Like you're going to have a fixed number of operations that you're going to be able to perform, and these operations all produce a fixed amount of memory usage, basically.
Yeah, another way to put it is that
So there is a limit, basically.
there are two kinds of limits. First is you have to pay for the size of the code. All right, this is one thing. If you allocate two larger structures, say, so indeed the stack can be small and you can have maps, very big maps for one entry in the stack. But if you want to use the stack, because if you create a stack and if it's big, it means that you went there and you actually wrote stuff in there, right? But this is very costly. So the bigger the stack in question, the higher the cost for you to allocate stuff in it. So there is, this is an incentive not to write too big data structure. You pay for access, you understand? You pay for all instructions.
Yes, but it's indirect. It might be
I
hard,
agree.
hard to estimate.
I agree with you.
No,
So you might need 1 million gas, or you might need 1,000,001 gas, and you only gave it 1 million, and you've wasted a whole request.
So yeah, there's basically that's I think you want to have an accurate estimation of how much gas your transaction is going to use so that it doesn't fail. Normally the client simulates your transaction when you're just about to send it, and it adds a little padding at the end to have a bit of extra in case something doesn't execute exactly in the same way in the real world.
Thank you. And then the equivalent one on the amount. What happens if there's a fairly complicated transaction? When we put the amount, and you said if it failed, we're charged anyway.
No, it's just the transaction fees that are.
It's a transaction fee.
Like the
Transaction fees are.
the money that you pay for the gas, basically, and for the baker to execute your contract.
Yeah.
So
It's just the postage stamp, you know, not the
So
contents of the envelope.
amount is just the gas.
No. Amount is the amount of money that you transfer,
Yes.
and you also have to pay a bit of extra for the postage stamp on your envelope, basically.
Right.
And that
Which is the
postage
gas.
stamp is burnt. I mean, it's lost if you.
It's for gas.
Oh,
If
so
the transaction fails.
it's only the gas that's burned.
Yes.
Okay.
Yes.
But the actual, I mean, if you're sending 1 million Tez or whatever to
Exactly.
somebody and the transaction fails, you won't lose the million. You will just use the paper on which it's
Right.
written.
Thank you.
Yes.
That's okay.
Something else? Before we move to LIGO, to show the difference, I really wanted to go through a small example. So yes, sometimes we have to go deeply in the stack. We had macros, so in fact the signs we saw earlier is not the real stack on when the program is actually deployed or originated, as we say in Tezos. These two are macros, so they're actually these are actually decomposed in other instructions. Okay, so it's actually bigger on the chain than this. It's not much bigger, I agree, but it's a bit larger than what we see before. And okay, so it's fun. Actually, many at Nomadic Labs like to write Michelson programs because it's fun. It's like a game. You have to find the shortest way to swap things, duplicate things, etc. And some people like it. I hope you notice that it's all in written like basic instructions for those of you who programmed in BASIC. So it's a caps lock alive and kicking. So where LIGO comes is that some of the problems I mean, difficulties in writing large and complex programs are, I hope, lifted by using a more high-level language than Michelson, and I will explain what it is exactly. So, like Michelson, actually, it's a programming language for writing smart contracts on Tezos. But unlike Michelson, LIGO looks like a mainstream language you will be familiar with, an algorithmic programming language, as opposed to perhaps a specific smart contract. But it's still a DSL, it's still domain-specific language, so it's aimed at writing smart contracts. So you would have, you wouldn't have all the bells and whistles and libraries that you would find, I don't know, in Python, for example. And you would also find some specific, we will see an example or two, or maybe more, of, you will have some primitives that are dealing with the blockchain itself. So it's a strange bird, but it's closer to a normal programming language. Okay, so we have a website for that is up for a month now, I think. So please go and check it out. It's quite nice. ligoland.org. It's important to remind that this is an open source project. It's a collective project. I will say a bit more later on about the organization aspect of it, because I think that may be of interest to you if you want to take part of it or ask questions. There's a tutorial, you can go there. And yes, about the name, well, it's fun to guess. If you don't know, ask me why later. So perhaps when you start with LIGO, the first striking thing is that it's not one syntax. We are used to think about Python or CAML we identify the language to the syntax. That's not the case with LIGO. We purposefully wanted to cater to different programmers that have been taught or are very savvy in, I don't know, Python or another one, and give them something familiar. So we had to start somewhere, and we started with things we thought were interesting to us to start with. So we started actually with two different syntaxes, and also not just syntaxes, but two different programming paradigms. So one is PascaLIGO, because it is inspired by Pascal. Of course, being the oldest folk in the team, I miss it. I miss it. So since I was the first to do it, I got my pick and I chose that. So it's imperative. Yeah, that's the perks of being the first, right? It's imperative. You have lots of keywords, and so of course, you can mutate values. And I will explain what I mean by locally. You have to annotate your values when you declare them, so you have to give the type. And then there is CameLIGO, which is inspired by a pure subset of OCaml. So here we have a functional language, a purely functional language, so no mutation. So you have to deal with constants, if you will. You still require type annotations. This is unlike most ML-like languages, where because they all feature almost full type inference. Here we don't do that. Maybe Georges can say more about the new type system we are working on. But at this stage, you still have to annotate, because we wanted to do a simple check instead of inferring the types. All right. But it has a very look, you will see the taste, it's very much OCaml-like, and this is very much like Pascal-like. And the idea is more to come, so we're not stopping here. So stay tuned for other syntax and maybe your favorite one, yes?
Are these languages designed, these variants designed so that you can switch from one to another easily, provably, safely? Or don't you care?
No, we do care.
Right.
We haven't implemented that, but yes, we thought about that. It's a bit tricky, but yes, because obviously what happens is that in the compiler we have different front ends. One is for PascaLIGO, this is for CameLIGO, and of course very quickly you arrive at the same internal representation for both of them, right? In theory, that gives us the possibility to start from PascaLIGO, go to the internal representation, and then come out with a pretty printer, if you will, to the other side. But it wouldn't be a very, straightforward pretty printer, because we have to understand that if you are using mutation here, okay, we have to find a way to not do it here, but still do it. So there are ways to do that. They are known. It's in the literature, but the problem, if we do it, it's maybe the program here will not be very recognizable. It will have the same semantics. Yes, we can ensure that. But perhaps it wouldn't be the one you would have written in the first place if you had started with this one.
And the other way is quite simple.
Yes, the other way is quite simple. Well, yes, simpler, much simpler. Yes.
Basically, if you look at decompilers for the .NET framework from Microsoft, you have a lot of decompilers to take your bytecode and print it as C#, Visual Basic, or F# or whatever. If you decompile it in a similar enough language, it looks fine. If you go from C# to F# or the other way around, it's not quite as idiomatic as you would expect it to be, because the languages have different ways of being usually used.
F# is functional,
yep.
C# is object-oriented.
So when you create, do you have to specify this is PascaLIGO?
Yes.
And this is a CameLIGO. It's not like
yes.
in C# where you've got elements of functional and imperative. It's more like you said, the .NET framework where you're writing this language, you're writing that language.
Yes, you have to make a choice here. Yes, you are right. This is different. You have to make a choice, but perhaps you don't have to commit forever to one choice. This is the very interesting question, and we thought about that, and we really want to do something like that. Yeah, because it's this strange idea of having many heads, right? Is I think it's to entice different kinds of programmers to try LIGO, right? And because we don't care so much about syntax, I mean, bike shedding is not helping. So people want to discuss, and I will show you that even for PascaLIGO, the examples I will show you, even in one, even in the future, I mean, there are many variants. For example, semicolons. How do you like your semicolons? Well, you can choose actually. See, we don't really care, but if you do care, it's fine with us. This is the idea. Some people do care a lot about these things, and then we tell them, okay, you can have it your way. We respect that, but and we will try hard to be able to read all your ways, but internally it will be the same. Yes?
So, would there be like use cases where you would say that PascaLIGO would suit better for writing a smart contract for this application, or CameLIGO would suit?
Yes. Well, this is tricky because when you design any programming language, you obviously have an idea, except perhaps C++, where they have all ideas, but you have an idea of what kind of applications you would like to build with that language, and so you make it easier, all right, to do it with that language. I have my own idea when I design these front ends, right? But I have no idea this will be the real reason people will use, because people will use it for their reasons, right? My idea was to contrast these two because they were different paradigms. Sorry. They look very different, a lot of keywords. My idea personally was why Pascal, because it's not just nostalgia, but it contains a lot of keywords. And some people, remember one thing we want for smart contracts is to be very readable. They have to be, ambiguity is the enemy here. And this is why also in Michelson, perhaps I didn't mention that, but it's in the slide, so you can go back to the slides. There are some strange and interesting constraints on the layout of Michelson programs about indentations, about the use or not use of UTF-8, where you could trick people in seeing things on the screen that are not there or hide things. Yes, so we have been very paranoid in the design of Michelson, right? Just here too, we want to perhaps not go as far, but if you want to be sure what you are saying, yes, keywords do help. And yes, you have to write begin and end, but then for each begin you have an end, and it can help some people. In CameLIGO, this is the functional style. You can open the construct and not close it. I mean, with a keyword. You can, it depends, right? This is a different approach. But my bet is that if you want to be you want to say everything very clearly, you should go for this one. If you are used to write loops, obviously you go to PascaLIGO. There are no loops here. Yes?
Do you have a compile time flag for CameLIGO to say, I insist that all opens must be closed, or begins must have ends?
No, well, no. Actually, okay, we are coming to that, but for PascaLIGO, because we are already flavors. But it's not a good idea. We want flags to be more consistent in one contract at least. But we were experimenting. So here is what it looks. The same contract looks like in PascaLIGO. Yeah, so, well, I don't know. It's pretty readable, no? I don't. We can declare types, and we have variables. My God, look at this. You can call it ballot, and it has a type, and we have a function here, and we have even a proper conditional, right? So this does exactly what. Oh, by the way, 1n is for the natural number 1, actually. I think in the Michelson I used int. This perhaps was a mistake. So we distinguish between them, but okay, it's the natural number. What can you show you? So yes, okay, so begin, end, everything has an end. I didn't use the convention of Pascal for returning a value, because if you know Pascal, the name of the function is a special variable, right? But what if you don't assign any value to that special variable and then you return? What are you returning? Obviously, this is not good. If you look at other languages like FL, they have a special. Anyway, I looked and I decided that the easiest way was to end with, and then you say what you want to end with. So sometimes you can put actually everything you want to do here, and we have an empty block. But at least it's defined. So that's clear. For example, here you can say that when this function ends, you will end with an empty list of operations and a store. And the store has been updated here. If everything went fine, you added 1 to the current ballot for that your choice of yours. Okay? So this is a departure from Pascal, which is not perfect, by the way. Pascal is not. This is much better. Come on, defining the return value is important. Of course, if you compile this with LIGO, PascaLIGO, with the option Pascal, the Michelson is not so neat as the one we had before. So it will be a bit bigger. And so this is also so the concern of cost of gas consumption was raised by the first designers of Michelson, because they said, okay, it's perhaps not very easy to think in terms of a stack, but at least you can control very finely and tune the cost of your program. It's true. But what we plan to do with LIGO is, it's actually what we don't want to do. We don't want to optimize. Not yet. We want to have the most straightforward translation to Michelson from here. So what you see here will be more or less what will be happening in Michelson. It's not about the semantics. The semantics will be, of course, the same, the Michelson and the source. But basically, the idea is that for I don't know, an assignment, you could perhaps not guess by yourself the real cost, but you will have an estimation. And I will talk about this when we talk about the tooling around LIGO. We plan to have a better estimation of the cost at the LIGO level. This is what it looks like in CameLIGO. So if you are familiar with OCaml, it looks very much like OCaml. It's not exactly that, because we have a special data type here for millions of Tez. But yeah, so for example here, if you do OCaml programming, you open a match construct and you don't close it. So you have to know where So you have to be aware that if you compose matches, what happened, right? Because if you open another match somewhere, you have to know what you're doing. Yes, it's tricky. So you have to put parentheses or anyway, it's up to you. Yes, so this is, what can I say, amount is predefined, map.update is predefined. It looks like we have a module system, but this is not the case. This is just, it's just a trick. Actually, this is one name, but we are thinking about having a module system for LIGO, not yet. So at the moment, one file is one contract, okay? All right, let's move perhaps to another more example. I wanted to give examples this time. So this is a simple crowdfunding contract. I found this in a paper about another language called Scylla, and I decided to do it here. So basically the idea is to have a contract that can be called in three different manners. So you have 3 entry points, as Arthur said before. One is for a backer to declare it, themselves, so send some funds before the deadline has passed, and only once, so you can send funds only one time. A backer can claim their funds after the deadline has passed and the goal has not been reached. It's typical crowdfunding, okay? And then the owner of the contract can withdraw the funds after the deadline has passed and the goal has been reached. Okay? And all of the cases are errors. Yes, that's very simple, but it's more complex than just voting. So here we need a store that is more complex because we need a record made of the goal to reach the deadline, which is a timestamp, the list, a map of a list of backers, which is a map from their address to the amount they sent. And we have a flag to say whether we are funded or not. The project has been funded or not. Okay. Now you can notice that we already have a flavor because here we opened and closed a compound construct using square brackets. So this is one flavor to do it instead of using begin ends or other constructs. And you notice that here I used the terminator semicolon. You cannot, if you are like a diehard fan of Pascal, you wouldn't write it. I wouldn't, but I know most of you young people, you would like it. So, in many places, you can enjoy your semicolons at the end without nothing afterwards, which is very weird to me, but okay. The function for sending, declare yourself as a backer. You start, so it's going to be about mutations. So you have, this means var, you annotate var, and you start with an empty list of operations. You will see that we're actually not creating new operations here. So I decided to put in every function. So you check that the current, so this is also a blockchain primitive. It's the same as in Michelson, actually. It's called now. It's a way to understand it's not the block number. We don't have that in accessible in Tezos, but it's a way to know when you are. You compare this to the deadline, and you look if you are behind or not. If you are still in time, you check. You check if the backer already sent money because we don't want to send twice. So if he didn't, so you check. Okay, the sender is a backer. No. Then you associate the amount. Remember, this is again a blockchain primitive. The amount is sent in a transaction when you call the contract. So you associate the sender to the amount in the storage. And there is a flavor. You can also write patch store backers with map, and this is one binding. Actually, I wanted to show you this because to show that there are flavors, and because here you can have a complex map, and you actually have a map here, and you can patch it with. You could have more bindings. You could make more changes than just one. See, this is one change, so this is shorter and looks better, right? Imagine you want to update many backers. It's not the case, but you could. This would be better in that case. You would put more of this here, okay? In one atomic operation. If the backer was already in the list, we do nothing. You can send money only once. And we end with no operations. and the store has been updated. Actually, the backers map has been updated here. Okay, it's very simple, but it gives you a taste of what it looks like. When you reclaim funds, it's a bit more involved, but it's interesting. Oh yes, this is interesting because we generate one operation. So we check if we are past the deadline or not. If the sender was not a backer, you cannot claim funds, obviously. If you indeed send funds before, we check whether the current balance of is more than the goal, or if already the crowdfunding has been funded, in which case the goal has been reached, so we can't refund you as well, right? It's a typical thing. Now, if you're in the case that it's none of these cases, then what we do is that we have a predefined function called transaction, and we create a transaction. So, okay, unit is not of interest here, but it means that we are going to send this amount to the sender. And this amount this is the one, okay? The one we found in the list of backers, right? So this amount is sent back to the sender, okay? And we know that's the right person because we know that they have been associated here, right? Yes? So we're not sending back money to someone else. And then we remove the sender from the map store backers, so you can claim twice. Otherwise, you could claim your funds twice. Yes? That's a good idea, but no. And this is for the owner of the contract to withdraw the funds after the crowdfunding has been successful. So if the person who calls the contract, which is in this case this function, this entry point, is indeed the owner, then if the present moment is past the deadline, and if the balance is more than the goal, okay, then we funded the project. All right. There is an alternative syntax. Okay, you understand now why I wanted to show you this. And then we can make a transaction from to send the current balance associated to the contract to the owner. Yeah. And we only have one, and so this is a list of transactions, which is only one. And that operation or list of operations is returned at the end. How about the store? Well, it doesn't matter. In this case, the store hasn't been changed, right? In this case, no change to the storage. Yes?
Change. Funded has been funded.
Right. No, you're right. You're right. I'm mistaken. Yes, you have to put the flag. And in the previous function, we check both conditions actually here, because we don't know if the owner of the crowdfunding has already, when this call happens, we don't know if the withdrawal has been called or not. So we cannot rely on one or the other condition. We have to check one or the other. This is why. So yes, you're right. We have to return the storage. Yes.
Coming up at least one level, what is to stop somebody asking for a refund twice at the same time, asking two different servers or some variation of that?
You can't do that because what happens is that, remember, it's not a real function call, so you actually issue a transaction to an address which is associated to the smart contract, okay? So this is a transaction in a block. So this is sequential. They are always treated sequentially. So there is no notion of having two transactions taking time at the same, validated at the same moment.
But the blockchain is distributed across thousands of machines.
Nevertheless, one block is sequential. So a block is made, among other things, of a list of transactions. And it's a list. It's a flat list. So if you have one call to this entry point, it's the first being validated.
Meaning it's not executed in parallel?
Nope.
But what's stopping it being executed in parallel? If it's distributed on 1,000 machines... It's
not distributed on 1,000 machines. It's re-executed by 1,000 machines. They all execute the same thing.
They all do the same thing.
Because they're cross-checking what the others did. But there's only one single execution step by step. That's the whole blockchain thing.
That's the same as the usual transactions. All what smart contracts do is, instead of transferring assets from A to B, which is the simplest transaction you can imagine, you want to have business logic in there and to perhaps transfer assets from A to C when some condition is met. Okay, this is basically, it's just business logic you want to put there instead of writing down forever that transfer from A to B. This is all it does. But other than that, it's just normal business as usual. So calling an entry point is just a transaction. So it's validated like any other transaction.
Normal business isn't done.
Confused by the description earlier was like of calling contracts as pure functions.
Yes.
Because I don't see how that can be on an ordered blockchain.
It's not completely pure in the sense that storage is mutated between calls, right? You want the storage associated to the contract is indeed modified and is persistent after each call. But if you look at the way this is written, it looks as if it's pure because we pass the storage as a parameter every time of the function. But indeed, what happens is that it's modified in the storage of the contract.
If you do have two almost concurrent transactions in the same block, and then they have to be ordered.
They have to be ordered. They have to be ordered.
Then what is the store that you're passing in? Because is the second transaction still the result of the first transaction? Is the first transaction still the result of the second transaction?
It's the same ordering that happens for any kind of transaction. This has nothing to do with smart contracts.
But if I'm calling the contract,
Yes.
and I have to pass in the store, right? I have to
No.
say,
No.
given the store is this.
No, you wouldn't. No. When you deploy the contract, you initialize the storage, and when you call the contract or activate it, you pass the parameter.
So you get around the problems of Ethereum on the tip sometimes.
Yeah.
You can.
Yes.
So it's pure a given state of storage, which you don't necessarily know when you first call it.
Yeah. At creation time, initialize the storage, and when you call, you pass the parameter. Did I miss something?
Yeah, that's actually an interesting way to put it.
Yes.
Basically, if you make a transaction and you pass some parameter, and I make a transaction at the same point in time and pass a parameter too, and let's say that the contract that we're calling is first person to call it gets 1,000 Tez and that's it. Okay. One of the transactions is going to get executed first.
Yeah.
Let's say that it's yours, so you get 1,000 Tez, and my transaction, which looked valid at the point where I emitted it on my computer, when it's executed on the blockchain, actually it's too late because there was basically a race condition.
Yes.
Now, when you're writing your smart contract, you want to think about these race conditions and try to avoid having stuff where you are specifying things inside the parameter that depend on the state of the storage.
Yeah.
Let's say, for example, that you have a list of participants in something in your contract,
Mm-hmm.
and in the parameter you're supposed to put the number of the cell in the list where you want to allocate yourself as a new participant. Let's say that there are 10 participants already, and you want to register yourself as the 11th participant. Okay. If you send as a parameter, oh, my name is George, and I'm number 11 now, and you send a transaction saying that your name is, I don't know, Michael, let's say, and you're also the 11th participant, then the contract is not really well designed because your transaction will fail and there was no reason for it to actually make it that way, right?
Mm-hmm.
The better way to do it would be for me to just send George and you send Michael, and as a result of the transaction, it prints out somewhere on your terminal, distributed application, web application, whatever, it prints out, oh, you got allocated the slot 11 and I got allocated the slot 12 or something. But if you build your smart contract in a way that it depends on the storage and you are going to have some pretty rapid exchanges on chain, then you will have contention like this and this will trigger problems.
And this is also true when a contract calls another one, which means, remember, this means that you issue an operation that is a specific transaction to activate another contract. It's not a function call here, right? This is different from what you do on Ethereum. Even though the storage is publicly readable by all the nodes on the network, there is no Michelson instruction to actually read the storage of another contract. And there is a reason for that, is that we wanted smart contracts in Michelson and actually in LIGO as well. to be as deterministic as possible. So we didn't want the smart contract behavior to be dependent on the state, the internal state, if you want, even if it's visible, of another contract. So this is another take on the issue. So when you have two contracts, this is also an issue. Right, and remember, when you issue so we don't call a contract like a function because this would be a function call with a stack. This is what Arthur explained. So you have to wait and come back, and you can have DAO attacks like this. You issue an operation that will be calling another contract at the end of the execution of your contract, and then if the execution is normal and ends here, then these operations are validated, all right, atomically. I think I say this some place in my slides. I wanted to say something specific, some peculiarities of LIGO. So beyond the fact that you have multiple syntaxes and functional or not functional, maybe we will have object-oriented. We mix. This is something that wasn't touched much before. Arthur said we had kind of lambdas in Michelson. In LIGO, I mean even in Michelson, they're not real lambdas. If you have done some Lisp or Scheme or Racket nowadays, called.
This is changing anyway.
This is changing. Okay, anyway. But the idea is that we have some, because we want to target Michelson, we have some constraints at LIGO as well, if we want to be efficient and rely on the native instructions. So we don't have the full-fledged. So we have an example that perhaps is not very obvious to you here, but so the idea is that when you call a function in LIGO, you actually are always copying your arguments you are sending to the function. Even though the function says that you can modify, so yes, for example, do we have an example here before? No, it's only the store every time. It's too bad. But so when you call a function, the arguments are duplicated. They can be mutated inside the functions, but this will not impact the caller. Okay, it's always copied. But even the environment is copied. So all the bindings at the function call, the side call, all those bindings are copied as well and frozen. And this is what the function will see when it's executed. It's a bit perhaps weird. And the example we have is here. So we have an accumulator that is initialized to 0. We have a function inside a function because this is what Pascal can do. What it does is just add a number to the accumulator, right? Nothing else. No, it's a pure side effect because we return unit. We don't have a value, meaningful value. And if you call aggregate with some integer, okay, this has no effect on the accumulator. This is very different from what you're used to. So why is that? Because when you call aggregate at this point, the value of ACK is frozen. It's bound to 0, right? At this point. Yes? Delta is an integer. Copying it will make no difference. So this is delta, but ACK is 0. So this copy of ACK will change, but it's different from that one. So locally you can mutate things, but this is all. The purpose is to return a meaningful value. So normally you should return something. This is meant to favor a programming style where you actually, when you call a function, it returns a value. And this value captures all that the caller has to know. All right? In that sense, there are no side effects. Only local to the function. So yes, locally you can have loops and whatnot. Yes, you can mutate all you want. But externally, nobody will know. It's a bit weird, but it's purposefully done that. Of course, there is an exception. If you want to call a specific function, which is an iterator, then the environment is not frozen. You want a side effect. That case. This is the exception. Anyway, I just wanted to mention that. Now, the interesting part is to talk about the future and what is going on now with LIGO. So we are working now on developing more tools around this language and compiler. One of them is to have an IDE We're experimenting with VS Code because of the plugin system that allows you to write plugins that are actually communicating with they're called language servers. But anyway, the idea is you can have plugins that are whose logic is written in any language you want, as long as you respect a specific protocol to talk to the IDE. All right, basically this is it. We want to have syntax highlighting, one-click compilation. We already have this in the command line, but we want to have dry runs. Dry run is when you want to experiment and play with your contract, but locally, and you don't want to run a real node, okay, and make a mistake or something. So you basically, at the same time, you send the parameter and the fee, you also send the storage. Because it's one dry run, it's not for real, all right? So it's not the normal workflow when you deploy on the blockchain where you deploy the contract, then you initialize the storage, and then you call the contract and you pass the parameter. Here you do all at once. It's called a dry run. Now, we want to have a reactive counter. We want people, when they're writing their legal code, they can have a counter that estimates the cost of, up to now, you are likely to pay in gas, okay? So for that, we are going to reuse the work that is being done at Nomadic Labs nowadays to have we are building statistical models to have a more accurate estimation of the gas consumption of instructions, which is very tricky to do. Currently, it's very conservative. So before deploying a contract, you have the client that talks to the node can do for you an estimation of the gas, but it's very conservative. We want to have a web-based IDE for people who don't even want to install a package on their computer, because sometimes they can't, especially in finance. I mean, it depends on your environment or your taste. So we are working also on a web-based IDE. It's a completely different architecture but we want the same set of features, all right? And another aspect I wanted to mention, yes, the third one is an SDK. Because in the end, what we want is not just people to write smart contracts in LIGO, but we want them to actually use them to build complex applications, distributed applications on Tezos. And for that, you need more than just a programming language. And we need to offer an SDK. So basically, what it means, it's a library with an interface that is clear, documented. So you can actually link with it, and then at a function call, a real function call from your language will mean something in terms of a contract or some transaction happening or something being done with a smart contract. So this is really important. So I think I mentioned, yes, smart wallets, web applications. We want people writing web applications it has to be easy for them to use a smart contract or just the blockchain as a database is easy nowadays to use if you're a web developer. What about R&D on the compiler itself? So just what's going on inside the compiler. So one thing that George is working on is actually to have a new powerful type system. The idea is to have more expressive contracts that are written, perhaps more concise, depending on the type system we will end having. We want to have more type inference. So we don't want to annotate perhaps everything, because that could be tedious, especially people familiar with OCaml that would choose to use CameLIGO. Perhaps they will be bothered by the fact that they have to actually annotate all their values. So some measure of type inference. And we want also to have a type system that will be able to check functional programs, imperative programs, and perhaps even object-oriented programs. But this will be the same framework. Currently, it's done separately somehow. George can say more about this at the end if you are interested. He is the expert on this. This is my actually area of expertise. I worked on the front end. Currently, there are two front ends, and it would be good to have a less technical depth and have a generic front end. So it's not just about only sharing code. It's really having perhaps one front end that looks like you have several of them. One funny thing I am working on is to try syntax extensions in contract. So inside the contract, you may want to use a special notation because you want to use it often. A bit like mathematicians, they start they say, I will write this relationship like that, and I will use the letter pi to mean something, right? So perhaps you would like to do that also in contracts, to be more compact. If you don't like a notation, you could also define your own. Another direction we are working on is to design a certified backend in Coq. Arthur mentioned certification earlier on, and the idea more precisely here is we have an intermediary language in the compiler, of course. So we lower the input language to this, and then we go down to Michelson. And we would like to, for the code generation, the generation of Michelson, having code generator that is proven correct. And even the code is extracted from the proof. The implementation, I didn't mention that, is of the compiler is done in OCaml. So if we use Coq, this is easy. I mean, we can extract to OCaml if you have a constructive proof of some property. Okay. So this is already very promising. Yeah, maybe you think, but what's the point? Perhaps you didn't ask. You're too polite, or it's too late. Sorry. The point is, it's more reliable. You don't need to know how that was achieved. Okay, but we can first. The maintainer of the compiler can be very confident that we won't have bugs in there. And if you trust us, that you also won't have them because it's the same compiler. Okay, it's formal methods is not about selling a mathematical proof to people who don't understand the mathematics. This is pointless. It's to sell the properties that things are going to be okay. These are not just good engineering or just marketing words. Right? You can check our credentials, you can check the code if you want, but it's more than words and more just than testing. It's proving, it's more powerful. Yes?
Can I just say and verify that what my understanding is the case, that you're saying it's not just a big sales thing to say it's proven, but I understand also that part of that is that you're making, if we look at it, you're making statements about its properties. And if somebody happened to have missed the property, and somebody else says, "Oh, of course, I assume you have this property,"
of course.
And it turns out a year later you only checked for 10 properties, not 12.
Exactly.
Then there can be a misunderstanding.
Of course.
Which sales spiel could expand
you are right.
The consequences of.
Yes, you are very right. Garbage in, garbage out applies here too, and arithmetics could be inconsistent, but at the moment planes are still flying and trains are. No, but this is true in mathematics as well, right? We have axioms. We have axioms. The idea is to have as less as possible axioms, and then you have also to have the right properties. This is true as well, because you prove properties. If you don't state the properties that are interesting to you, well, you obviously miss something. You are under-specifying. But having axioms, this is unavoidable. The less, the better, of course. And of course, you're right, properties, you have to think of what are the properties that you want to prove. This is very true.
It's the client's responsibility to make sure all the properties are in.
Well, yes, indeed. And these can be explained in sometimes, they can be explained, actually. I mean, the proof is much more complicated than the statement of the property. And I believe in that too. We can advertise that. All right. But again, I think I'm the only one in the... so I'm going to speak about LIGO and the company side. But the people behind LIGO, I think I'm the only one having a PhD. So you don't have to be think that this is only a research thing or it's a problem if you don't have a PhD. That's not the case at all. And now the team. What's happening is that George and I, we are, so the idea of LIGO actually started in my mind, and also Gabriel, who is not here today. And so he created the company. got funded by the Tezos Foundation, and George and I were going to jump ships, although there is a partnership between Nomadic Labs and the company behind LIGO, so practically it won't change much. But this is important to know. It's an international team. 5 of us are in Paris, and we have 8 contractors that spread around the world. But it's a real team. So whether you're a contractor or not, it makes no difference. I became recently the COO, so now I'm suddenly very tired and busy, and I miss programming already. But it has to be done. And just one slide about Marigold, and we're done. I'm sorry, it's a bit long, but you had many interesting questions. So Marigold is actually the layer 2 part of this, and unfortunately this is the part I don't know very well, so I've been instructed to tell you that kind of thing. I think Arthur can actually say something about this if you ask him. Layer 2 means that you want to have a greater throughput on the blockchain. There are things that are expensive, that take time. And sometimes this is called off-chain, but this is not the proper name. And perhaps you have heard, because many of you, if you come from Ethereum, you have heard of Plasma, I'm sure. So it's a way to do, instead of assuming that the blockchain is based on the assumption that you want peers that don't know each other, that don't trust each other, to still be able to agree, all right, on some transaction or even a contract, okay? But in many cases, as Arthur said, people can decide to trust each other. And then we could use the blockchain in case there is a disagreement. So this is basically the idea. You would use the blockchain for what it's good at, which is being an arbiter of a disagreement, but not assume that everyone would be untrustworthy from the start. In that case, we assume that people trust each other, then they do that business not on the chain, somewhere else, and there's a mechanism to, in case of disagreement, to go back to the blockchain. This is the basic idea. Arthur mentioned, yes, meta consensus is the meta rules he mentioned earlier, so the voting system. So we can change the protocol to actually change things that, for example, make the compilation of LIGO to Michelson more faster. So in Babylon, there is a proposal that was made by George to add new instructions to fetch cheaply, I mean, more cheaply than nowadays, data in the stack of Michelson. And then just I wanted to mention, yes, this company, I was told to mention it in Japan. They are working on, and I don't know what it means, but it's called General Plasma, so I suppose it's good. It's for people who want to have a larger class of contract that just having tokens on top of Tezos. Arthur can say much more things about this if he wants. Just to make this clear, I don't even know what NST means, sorry.
Well, it's supposed to be an F.
It's an F? Oh my goodness, all right.
Non-fungible.
Oh,
Non-fungible. Yes, okay, sorry.
When you said plasma, do you mean Ethereum plasma?
It's the same idea. Arthur, can you help me out here?
Yeah, so I'll help with the terminology. So, yes, the idea in, I think the idea of plasma was first published by Marigold and Jopun when they were introducing MySQL. And, oops, thank you. And they were calling it plasma at the time. And the term of art which has emerged to describe plasma-like technology is commit chains. So you have state channels and commit chains, and there are different things. So hang on, let me just hang this first.
Just while you're doing that, could you go back one slide? We'll do it.
Right. This one?
Yeah.
Yeah.
We'll make this available to you at some point.
I can explain briefly the difference. So let's start with the state channel because that's the easier one of the two. So the state channel is, let's say you and I want to play a game of chess, for example, and we could encode the rules of chess in a smart contract. And then I would make a move on the chain, and then you wait for all the confirmations, and then you make a move. And it's very, very slow. So what we're going to do instead is we're going to tell the chain that, you know what, we're about to play a game of chess. And maybe all we put is like some hash on the chain of the rules of chess, for example. And then we put some money in the smart contracts in escrow. And then your computer and my computer start playing chess with each other. So I sign the moves that I want to make, and then you receive it. It's a valid move. Then you make another move on top of that. You sign it. You send it to me. And so we send each other back and forth signed messages. Now that's super fast. That's just over the internet. There's no consensus. There's no blockchain. Very, very fast. We just keep signing and counter-signing the same documents by making small edits to it. And in a perfect world, at the end of this, I just maybe I loot the game and I decide to pay you because we bet on the outcome of the game. So I send you the payment, and everyone was honest and everything was great. Now maybe you try to play an invalid move in this game of chess, and then in that case, what I'm going to do is I'm going to take the message you sent me, which contains an invalid move, which was signed by you, and I'm going to bring it to the smart contract on the chain. And I'm going to say, hey, here's the rules we were playing by, and here's what this person did, and here's why. And if you execute this code, which verifies the move is valid, then you will see that it was an invalid move, and then it will be forfeited. So in that case, we've just used a chain as an adjudication mechanism. And the nice thing is, you never use a chain because there's never an incentive for the person to try and cheat you, because then you're going to lose their money either way. Maybe they lose even more if they try to cheat. So you have it has the safety of the chain, but the ease of just doing this by yourself. And so if you look at something like Lightning Network, for example, it's very much like that. We open a channel with each other, and then I sign it, you sign it, I sign it, you sign it. And then if for some reason you disappear or you sign the wrong thing, I could just go to the channel and get the money back. So that's a state channel. That works really well when you have just two people. And so that's why Lightning Network kind of works as a graph of peer relationship, but it's also very capital inefficient, because if I want to send money to someone and I'm not directly connected to them, then we're going to need to use all the capital that's in the chain between the two of us. So the idea of commit chains is easier than that. So imagine a blockchain with its own rules, but in this case, let's say this chain is just run by a single party. It doesn't have to be a single party. Maybe it's just like, I don't know, maybe you have seven peers to be, and they run some BFT algorithm. So very, very centralized solution. And you have this chain, and then we all happily use this chain. But we don't really trust those 7 parties because it's very centralized. Maybe they can try to cheat us. But we still do our trades, and what happens is the 7 parties, they go on the main blockchain and they post a hash of whatever the content of the ledger is regularly. And then the set of participants in this commit chain, they still watch what's going on. Maybe there's a website, and maybe the content of the blocks is published on a website, and they verify that the blocks are published, and they verify that the blocks are valid, and everything seems on the up and up. But for some reason, they decide to stop producing the blocks. They don't display the block, or they display an invalid block. And at that point, what you can do is you will go on the chain to the main smart contract and say that block transition was invalid. These people, they didn't produce a block, and you will basically say, hey, hang on, let me get the funds that I had as of the last valid block that was posted on this chain and get my funds out. And so if you move some funds from the smart contracts into this other chain, you have a mechanism for getting out. And so in some sense, some of the states, it's hard to rescue all of the state, but at least you can rescue the funds. And it's very costly because everyone needs to exit at the same time, so there's difficulties around that. But basically the idea is very similar to the state channel. The philosophy is very similar in the sense of like, let's do everything in an environment where there's going to be trust involved. And if there's a breakdown of trust, we will have enough cryptographic evidence that we can take on the main chain to make to rectify whatever happened off chain. So yeah, state channel is very easy, very convenient when you have 2, 3 parties, maybe a small amount of parties. Commit chains, it's more when you have a lot of activity and many participants. That's why they were. I think they're great for things like games, for example. Things like decentralized exchanges, this type of applications make a lot of sense in commit chains. I don't. Do you have any other questions?
I got a couple. So to Christian,
Yes.
so you got 13 people in the team.
Yes.
So some of the stuff sounds quite ambitious.
Yes, it does.
How far would you say you're?
And we are all tired, if you want to know. Sorry.
How far are you through, and how far do you think you've got to go?
All right. Okay. Let's go back then. Currently, okay. So there is work already just that started or currently just started on this, and that I don't think the SDK is already there. The compiler is obviously the thing that has been more worked. And the website and the tutorial, because this was the first thing to communicate and having something that people can play with, even if it's without any extra tooling. This already started. George can tell you a lot about this. The backend is the certified backend in Coq is already underway. So. And there are things I don't even know yet, but some people. But it's pretty much all there is. You can follow us. We are on Slack. We have a channel. It's public, I think. It's LIGO. Yes, LIGO is public, so you can go there. You can meet us in Paris and even in Washington State. I mean, we are in many places.
Do you have an office in London?
Nope, we don't have offices. We are squatting. Sorry?
World capital, no office.
Anyway, London is closer to Paris than Bordeaux is to Paris, so I always think it that way. It's no, but we perhaps at one point we will have to have offices in some place, and I will consider London then.
Well, now that I've you should have one.
Yes, indeed, that's very true.
It's going to be fine. Justin.
They'll stop the Euro.
No. There are no frontiers for like-minded people like us. But yes, at one point we will have to have a real offices and name on the door. But at the moment we focus on the technology. So plus we have a partnership with Nomadic Labs. It's not going to change much in practice. We're still very close to them, especially George, I, and Gabriel, who were next month, George and I, we are going to change companies, but in practice, it means, okay. But we have been committed to LIGO for many months already, since January, for example, in our case.
And the other question was how you funded?
It's the Tezos Foundation, so there was a grant at the end of last year, I think, and so this is how it is funded.
How much?
I don't know that. I should know, but I don't know yet. I'm catching up with everything now. I used to be a programmer 2 weeks ago, you know. I've been for 25 years, and so yes, I don't know yet. But I think is it public? Arthur, does the foundation communicate? I have no idea if it's. I don't know. I will ask now.
One of the first.
I should have asked before quitting. Yes.
Are you going to do a Go flavour of LIGO? We call it PascaLIGO or LIGO Go.
That's a good one. That's a very good one. Maybe it's as I said. If you want something, you can. You must be willing to program, and I can coach you, especially for the front end. Yes.
PHP or P++?
It would be good to have
C++ is unparsable or Turing complete, whatever.
to have a Lisp such as Clojure, because then you get homoiconicity.
We'll talk about Lisp over beer.
You get.
He likes it very much.
For everybody, the advantages you get the data and the code are exactly the same structure.
Yes, indeed, I know.
As distinct, so you don't get these very different sugars. It's one thing. So.
I'm hearing George speaking now.
Yes.
Yeah, yes, I know. Yeah, maybe it's that's a good thing. This is just a skin, but it has to be written. The code has to be written, and we need something more generic for the front end. This is also I'm working on, because we don't want to duplicate many things. But yes, we want to have that. and we want to have better error messages as well, and so on. I mean, we really want to make it easy for people to write code. Yes.
Did you consider, are you considering to running the surveys with the developers, like with all really popular languages? They always run surveys.
This was considered at one time, I remember. I don't know if this was abandoned completely or not.
Actually,
I'm not sure.
I can help with that because we are running one. We will run
Oh,
actually. So,
right.
So even with the other cryptocurrencies, so maybe we can get some feedback and get
Yes.
some adoption.
Yeah, that would be interesting. I think Gabriel has a very clear idea of what he wants. But yeah, why not? It's a good idea. All right. Okay. One more. Really? What?
Sorry, Barry. Do you mind to not touch the mic? Yeah.
It's not?
Yeah. Don't. Yeah. Just leave it on. Just leave it on. Yeah. No. It's great. Just leave it on. It just because you touch it, if I can hear it. Yeah.
Oh my goodness!
Yeah,
This is
it's
what you
alright.
were. All right. I'm not used to that.
Yeah. Don't worry.
All right. I have to look
One
more.
last question, guys.
Yes, there was one on the back or two. I don't know. Go ahead.
The operations that you return at the end,
Yes.
that's like basically like a land you've constructed with some parameters, right?
Operations, I think it's explained in the slide. It's I didn't because I didn't want. There's a lot of stuff here. There are basically of three kinds. There can be a normal transaction with exchange of assets. Okay, where is it? It's somewhere. Wait. Yes, operations may have been returned. So these could be transactions. Send some tokens from A to B. You could have a contract creation, so a contract can create another contract. You can also have delegate settings. And I think in contract creations, this includes the contract activations or calling another contract as well. So, and then what is important is that after the contract runs, produces operations, these transactions are also validated atomically. So they are done. They are validated after the transaction that is the contract call, if you will, is finished. Then you have these transactions that are immediately validated just afterwards.
So I guess what I was wondering is that are they like easily serializable or canonizable or canonicalizable so that you could, like another contract could actually examine the operations in respect?
I don't think so. Yeah, that's one of the things in Michelson. Basically, the thing is that if you are making a transfer of tokens to another contract, and that other contract is expecting a parameter which is a string, for example, the name of the person you're voting for, okay? Then inside the transaction that you are making, it's kind of embeds the type of the contract that you are calling. Namely, you are transferring some tokens and a string to a contract that expects a string, right? So you have the amount, the string, and the address of the contract. And if you're calling a contract that expects a boolean, like turn on or off the light, something like this, then you're going to have the amount that you're transferring, the boolean, and the address of the contract. And if you wanted to have a list of operations that you could inspect, it means that you would have a list where the elements are sometimes stuff with a string, sometimes stuff with a boolean, or sometimes stuff with whatever the parameter of that contract is. And that doesn't fit well in the type system of Michelson. So basically, when you create the transaction, when you create the operation, it just gets boxed into a black box and you can't examine it afterwards because of that type system restriction.
But maybe someone will build new type into Tezos.
Well, this is what he's working on, at least for LIGO, because we have more
for LIGO,
we have more.
This is a limitation of Michelson. It would be right now a bit difficult to circumvent, but it's something that if it's needed can be considered. Or there are ways to do it.
Yeah. I think even Arthur mentioned that with TA and TB, right? The way to encode one entry point or the other. This is
this is like a similar limitation of
Michelson
that was lifted in the latest amendment.
Yes.
Proposal, sorry.
Proposal.
It wasn't really a semi-standard to use these annotations or to code multiple entry points. It just basically solidifies what has been a practice of smart contracts and make it more more usable. It's really useful. If you know exactly what contract you're calling, it's not that useful because you could have already called it this way.
Yeah.
It's very useful when you want to create standard interfaces for contracts.
Yes.
Standard token types, for example.
Mhm. Someone wanted to ask something. I remember this way. You want?
Just had some questions, but maybe more generally on Tezos.
Oh.
Is it possible, like maybe kind of more?
Well,
I can give a general solution.
yes.
What are the next big
It's very good at this.
I've done it a lot. All right. Yes.
So, like, what are the next big things to expect? I heard actually Nomadic Lab suggested that takes a lot of implementation or something. Are you guys working on that?
So I don't work for Nomadic Labs, but I can tell you a little bit about ZK Snarks. Like personally, one of the things I'm excited about in the space of cryptocurrencies is the ability to have private transactions, and this is really not easy. Let me explain why. So if you have a decentralized network representing a cryptocurrency, you're making you have to solve the double spend problem where I give you evidence that I signed over some coins to you. Now that's easy. There's a digital signature part. It's been known since the 70s. But the problem is that what if I sign the same check over to two people? I sign it twice. And the way that Bitcoin solves this is basically by saying you're only going to accept a signature. You're going to only accept a transaction if it's been posted on a global store that everyone can see. So basically the idea is like, how do I know you're not spending this transaction, you haven't spent this transaction twice? Because I'm going to look in this space and everyone in the world is going to have access to the list of every single transaction and is going to be able to make sure that this transaction hasn't happened twice in this ledger. Like that's a very, 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 very strong condition. Like basically the ability to solve the double spending problem is by making everything public. It makes it very, very hard to do private transactions. Very, very hard. And the way that you solve this using a cryptographic technique known as snarks is that you essentially reduce the proof to the minimum, to the smallest statement you can make. And the way it works essentially is you have some coins and then you hide them inside a commitment. And you have a large tree of commitments which is maintained by the nodes in a network. And then when you want to spend it, what you do is say, well, in that list of hidden commitments lies one of the commitments that I have made, but you're not revealing which one. So in some sense, it's like everything is public, but everything is encrypted. It's kind of like working with an encrypted set of transactions and saying, one of these is mine, and I haven't spent it, and haven't spent it before, and here's the proof. So zero knowledge proofs. This is the most generic way of getting privacy. There's other techniques for privacy on chain. People talk about Monero. People got irrationally excited about Mimblewimble as a privacy technology. It's not good privacy. Like you have much stronger privacy in Monero than in Mimblewimble, for example, and you have much stronger privacy in some in a system like Zcash than you can obtain in Monero. It's complicated cryptography, it's complicated mathematics, so it has not been yet widely deployed. And indeed, one of the interesting proposals that can be made, and I think there are people working on this at Nomadic Labs, is integrating the work that was done on Zcash and make it available for Tezos, not just for the native token Tez of Tezos, but also for any token contract which is being created on the chain, make that available.
It's pretty cool.
It's very cool. Yeah, the question.
Yeah, I have a last generic question actually about Tezos.
Yeah.
So I've seen on YouTube that apparently there is not a predefined roadmap for Tezos, but you don't have like a sort of step release.
Define you.
Pardon?
Define you.
Tezos, like the project.
What is Tezos?
slide one.
And the technology.
Well, how would the technology have a roadmap? Sorry, I'm going to be very Socratic, but this brings me back to my first point. Well, Tezos is a piece of technology. It cannot have a roadmap. People have roadmaps.
Yeah, no, yeah, okay. I'm just proving this point.
What?
I got the answer already.
Yeah, but like I can rephrase your question in a way that makes sense, but I think it's more instructive if we get to the core of it. So Tezos is not an organization; it's a technology. An organization could have a roadmap, but Tezos is not an organization, therefore it doesn't have a roadmap. Now, Nomadic probably has a roadmap. Marigold has a roadmap. Like in my mind, I have like my ideal roadmap of like how this might play out, but different people have different roadmaps. Talking about the roadmap, the problem is not the word roadmap, it's the word the. Because when you say the roadmap, it implies that there's a canonical one. And there's no canonical one, it's the entire point of the project. The entire point of the project is that you don't have the central development team that sets a roadmap, is that anyone can contribute changes to the protocol. Anyone can come in and have their own version, and the versions which are being proposed, the patches, the proposals, they have to be adopted by the network. And so that's the reason why I think that the answer is not like there is no roadmap. It's more like the question dissolves itself once you try to think about what is Tezos, what is the roadmap.
So what's your role these days?
Mostly I do these things. I answer general question about Tezos. I try to do
Advocacy, awareness building, this kind of stuff.
Advocacy, awareness building, trying to think about the technology, trying to think about the core protocol, bouncing ideas with people who work on the core protocol, people who work on layer 2 solutions. So I talk to people at Marigold, I talk to people at Nomadic, I talk to people at Obsidian and Cryptonomic. And I try to also make sure that people talk to each other, people know what's going on in the space. Just give you one thing. There's a company in Japan called DaiLambda. They're releasing a new storage method for Tezos called Plebeia, which is about 10 times more efficient than the existing one, and can do very short proofs. And that's based on a code that I originally built last year. So I do a lot of these things and try to pollinate as much as I can.
So who is a good person to contact to talk about use cases, existing use cases, and possible future use cases that might fit in with what's being done? So
if you want to use the Tezos blockchain, well, there's several people you could contact. There are some entities which are engaging with people building use cases on the Tezos blockchain. One of these is the Tocqueville group, for example, which is in New York. There are other groups in France that also do that specifically for the Francophone sphere. You could also directly engage with the communities. There are forums such as Reddit, Riot. It all depends on what you're looking for. And yes, it's a kind of like big and patchy ecosystem. It can be hard to navigate because it's not like there's someone you can turn to that will have all of the answers.
It's not centralized.
It's part of it's cost of not being
But that's a very good segue to
right.
just wrapping up. Thank you very much. So we will actually in a couple of months have a more hands-on session with Marigold and LIGO. We just have yet to plan the roadmap. So
with which flavor of LIGO?
The one you like.
Take a vote on it.
We really don't care.
Yes.
No, but the hands-on, I assume there's going to be one of them, right? Somebody's going to fit by the show.
We'll see. We'll see.
Surprise.
Down on LIGO.
We will see.
Yes.
I don't know. Maybe you. I don't know.
Okay.
You could have two helpers and then...
Exactly. I was thinking about that actually.
Just like to give just 5 minutes, just a quick wrap up. Just as so, we had a really good overview of a lot of the very, very complicated, more deep levels of Tezos. But just to explain a few of the cases as well that exist as well. So at the moment I'm representing Tezos Commons as well here in Tezos UK. And you can also work at your own pace with some curriculum to start getting into Tezos. That's tezoscapstone.com. You don't need any.
Can you go back to the slide?
Yes, of course.
I love that.
It's a very nice logo.
Who did that?
It was Tezos Commons. So there's also the Zastrian program as well, where you can also design a voting app as well. And it uses the latest Truffle plugin, which will eventually have Tezos added. It's on the roadmap. So if you start using Truffle, then you can also start to experience what it's like to write dApps. One place where you can ask questions, of course, is tezos.stackexchange.com, but this is by no means the only place you can ask questions. Reach out to different communities, different organizations, as well, different companies. Slack channels, there is one, we actually have one as well with work on blockchain as well. And some of the use cases that are out there already implemented, they cover pretty much most of the industries that you'd expect, from real estate, insurance, even in automotive, due diligence, so where money is going, as well as some other more ambitious projects, which include legal terminology encoded into smart contracts, and of course the standard P2P lending. Really what I'm up here to say today is please come to our hands-on event on Saturday. It starts at 9, that's where you can get help to set up your environments. Danny will be there, and also, can we say? No? Okay. He will be spending more time with Tezos, the technology, and but he will help also with the environment, your environments to set up. There are instructions on the meetup, so please have a look at that. And then Mike from Cryptonomic is coming all the way from New York to explain their dev tools, which also help you get started with Tezos very, very, very quickly. Without further ado, I say thank you again, once again, to our guests. Round of applause, please. And yes, thank you again for coming.
Yeah.
Make sure you